Welcome back, dear students. So in this session, you will be learning about what Joule-Thomson coefficient is, what is its importance, and how to calculate the Joule-Thomson coefficient, and how to determine whether the throttling process will actually provide cooling or not. Okay, so let us move on to the subject straight away. The Joule-Thomson coefficient. Again, a gentle reminder, if you are not yet subscribed, please do subscribe to my channel to get all interesting upcoming videos on mechanical engineering. So, you know what is a throttling process, right? You're familiar with it in the refrigeration system, also under steady flow devices in open systems. We have learned that there is a process in which the enthalpy remains constant. The initial and final enthalpy of the substance will be the same. So let us examine the case of a throttling valve. Fine. So the temperature, the pressure obviously during a throttling process would get reduced. Always the pressure will get reduced when throttling is done. But that is not the case with the temperature. Temperature may increase or decrease or remain the same depending on the initial temperature of the fluid. There are so many factors to be considered whether we can achieve temperature reduction or not in the throttling process. So let us discuss that in detail. So Joule-Thomson coefficient, which is usually represented by mu Jt or simply mu in thermodynamics, is a measure of the change in temperature with pressure. Change in temperature with pressure during a constant enthalpy process. Joule-Thomson coefficient is a measure of change in temperature with respect to pressure, that is dou T by dou P at constant enthalpy process. That is the process taking place in a throttling device. Now the value of Joule-Thomson coefficient mu or mu Jt can be equal to 0, less than 0 or greater than 0 depending on temperature remains constant. If mu Jt is equal to 0, that means the temperature does not change during a throttling process. If the Joule-Thomson coefficient is greater than 0, the value of mu is greater than 0, there is a temperature reduction. If the value of Joule-Thomson coefficient is less than 0, there is a temperature increase during throttling. So we are not achieved the throttling actually. Pressure obviously will be reduced, but the temperature reduction or temperature hike will be decided depending on the mu value, that is a Joule-Thomson coefficient value, that is a measure of reduction of change in temperature with respect to pressure. Now let us examine how to calculate the Joule-Thomson coefficient, what experiment is done to get this Joule-Thomson coefficient for different sizes and for different fluids. Let us see that in detail. Let us take a porous plug. Okay, let us take a porous plug, simply a fixed dimension porous plug in which the initial conditions are represented by pressure P1 and temperature T1, and the final conditions depending on the type of the porous plug, dimension of the porous plug, as well as the duration. It will be P2 and T2, that will be varying, right? So we are going to conduct an experiment and we are going to plot the variation of temperature and pressure on a PT diagram. So repeating the experiments on different sizes of porous plugs. Okay, different sizes of. So initially, for a particular pressure and temperature value, the final pressure and temperature is calculated and noting down the value, and repeating the experiment for different sizes of porous plug and plotting the variation, you will get a curve like this. inlet state being fixed. P1 and T1 are fixed initially, and the final states, exit states, are plotted. These points are obtained for different sizes of porous plugs. For the one size of porous plug, this is the point, and the second size, this is the exit state. And in any case, you know that the process that takes place in a porous plug, that is a throttling device, is an isenthalpic process. Enthalpy remains constant, right? So when you join the various points, that is the initial state with different end states, you will get a curve like this. For different sizes of porous plugs, measuring the outlet temperature for a fixed inlet temperature. Okay, so depending on the size of the porous plug, the temperature may increase or decrease. You know that up to this point that there is a temperature increase. Then thereafter, the slope becomes 0, and finally there is a temperature reduction, right? Now, based on this curve, this TP diagram, we are going to learn the Joule-Thomson coefficient and so many terms associated with that. Now, we are going to repeat the experiment for different sets of inlet pressure and temperature. So far, we have done for a fixed temperature and pressure, and by varying the size of the porous plugs. Now, we are going to repeat the experiment for different sets of inlet pressure and temperature. And plotting the results, you will get different constant enthalpy lines, right? Obviously, you will get different constant enthalpy lines like this. At a particular point on each constant enthalpy line, you can see that the slope will be 0. That is a dou T by dou P, mu Jt, or dou T by dou P. The slope of the isenthalpic line will be 0 at a particular point on each constant enthalpy line. So if you join those points and plot a curve, that line is called inversion line. So inversion line is the line joining the 0 slope on the isenthalpic lines. And you can see that that inversion line will meet the ordinate where P is equal to 0, known as maximum inversion temperature. Maximum inversion temperature. And this inversion curve is inversion line or inversion curve is a very important line on the study of Joule-Thomson coefficient and the throttling process, because on the right hand side of the inversion line you can see that mu Jt less than 0. That means there is a temperature increase during throttling. When the pressure is reduced, temperature will increase on the right hand side of the inversion line. On the left hand side of the inversion line you can see that mu Jt greater than 0. That means there is a temperature reduction when the pressure is reduced. So our idea will be to cool the fluid below its inversion temperature in order to achieve the throttling temperature reduction. So these are the important terms associated with Joule-Thomson coefficient. Inversion line, the line passes through the 0 slope on constant enthalpy lines or isenthalpic lines. Inversion temperature is a temperature at a point where constant enthalpy line intersect the inversion line. Constant enthalpy line intersect the inversion line. Maximum inversion temperature is the meeting point of inversion line with the ordinate, or P is equal to 0 line. So from the Joule-Thomson coefficient and the inversion line plot, it is evident that the cooling effect cannot be achieved by throttling process unless the fluid is below its maximum inversion temperature. Each and every fluid will be having a maximum inversion temperature. If you not cooled the fluid below its maximum inversion temperature, cooling cannot be achieved. Otherwise, the heating will be taking place during the throttling process. For example, if you take the case of hydrogen, okay, hydrogen gas, the maximum inversion temperature is minus 68 degrees Celsius. So you must cool hydrogen below this temperature if you want to achieve a cooling during throttling. Otherwise, obviously, heating will be the result. The temperature will be increased during the throttling process. So this Joule-Thomson coefficient and JT valves working on the principle of this Joule-Thomson coefficient has significant role to play in cryogenics, low temperature achievement, which is the topic for study in the upcoming classes. So till then, it's goodbye and thank you for watching. If you are not subscribed, please do it and keep watching the upcoming lectures for interesting lectures on cryogenics. If you are really interested to know cryogenics fundamentals and various liquefaction processes, let us learn that together in the upcoming sessions. Thank you so much.